Welcome to the discussion of impulse and momentum. This is Chapter 6, in which we continue our dynamics discussion of the principles of mechanics. Recall that in the first few chapters we were looking at the description of motion in terms of position, time, velocity, and acceleration, and then we introduced dynamics of motion, which brought into play the causes of motion through Newton's second law, F equals ma. We then expanded on that as we brought work and energy into the problem and looked at the definitions of work, kinetic energy, potential energy, as well as the conservation of energy principle. Finally, in this chapter, we look at one final concept in linear motion, and that is the concept of momentum, which is related to the object's inertia. So let's continue. Our objective in this study is to understand the definition of momentum, what momentum means, and then to use momentum in the analysis of collisions and interactions. First of all, let's begin by starting with Newton's second law. And that's our old friend F equals ma. We can rewrite Newton's second law in this form using the definition of acceleration as a change in velocity over change in time. Now, under the circumstance where the mass of the object is not changing, it doesn't matter whether the mass is placed in front of the change symbol or behind the change symbol, because the mass is not changing. Therefore, the operation of the delta change symbol will not affect that mass. So in such case, we can go ahead and move the mass next to the velocity, and we see we have a combined pair of symbols there, mass times velocity, which we're going to just simply re-express as the symbol p, which is defined as the momentum. And so we have an alternate expression for Newton's second law, which says that a force is responsible for the rate of change of a quantity now expressed as momentum, which is the product of mass times velocity. Since we utilize the measure of mass as a measure of inertia, in other words, inertia being the resistance to being accelerated, resistance to change in the state of motion of the object, in Newton's first law, you recall, it was stated that an object remains at rest unless acted upon by a force, and an object continues in straight line motion unless acted upon by a force. And we express that resistance to the change in the state of motion of the object as the inertia, and that the inertia is measured by measuring mass. And therefore we can see that the definition of momentum, by incorporating the mass in there, is actually an expression of the inertia that an object has. And therefore changing the inertia requires a force. This is a useful expression because it gives us a way of looking at problems from the concept of momentum as opposed to the idea of acceleration. And note that this is a property of the object, the mass m, and that mass is what's experiencing the application of forces, which is resulting in that momentum changing. Now, because of that relationship, let's bring it over here and look at this, where we have taken the delta t, the change in time, from underneath the delta p and brought it over across the equal sign next to the force. And what this says is the left-hand side is expressing for you the application of a force for a certain duration of time. And the result of that application of that force for that duration of time is that the momentum is changing from some original value P0 to some final value Pf. Now what if, in fact, there were no external force? In other words, the object under interest was not experiencing a net external force on it. In that case, we'd see that the left-hand side is 0, and then 0 is the difference between the final and initial momentum, which means that the momentum itself has not changed. Which means that the final momentum and the initial momentum are the same for this object. Well, that makes perfect sense if you're thinking about, say, an object which is moving along, such as a ball moving along in a straight line, and its momentum is its mass times its velocity. And if there's no external force acting on this ball, then that velocity stays the same regardless of where we look at it, and therefore its mass times velocity, which is its momentum, at some point 0 is the same as it is at some point f later on. And that makes perfect sense. The utility of this is that it's broader than that. In other words, the conservation of momentum principle says that the total momentum of a system, which could be a group of particles that are interacting only amongst themselves but without external interaction, that group of particles also must conserve momentum. Even though they may be colliding with each other in the process of collision, the momentum of the entire system will stay constant. Now, that's what we mean by a collision. And let's simplify this to a collision of just two particles. These two particles can be considered as to being isolated all by themselves with no external forces present. As a result, the conservation of momentum theorem tells us that whatever happens between them, for instance, as they collide, the momentum they have in total before collision, which is the product of the mass of each one times its vector velocity, that momentum must be equal to the momentum after they have collided, and seen here as moving apart. So that gives us a way to connect these two situations before and after by the conservation of momentum theorem principle. Now, we must obviously we'd have to know some information. In other words, if we knew the velocities at which they approached each other and their masses, we would have a value for this initial momentum. And if we measured one of the outgoing velocities, we already know their masses, then that means we know the fourth one because these two things are connected by the conservation of momentum principle. And the conservation of momentum says before collision and after collision, or even if we're talking interaction. In other words, they don't actually have to touch. They can be interacting by forces that act at a distance, such as gravity or magnetism or electrostatics, and their momentum before and after is constant. So these are vectors, so we're still going to have to use our formalism of vector algebra when we're doing momentum problems, such that if you're moving to the right, we'll call that positive velocity, moving to the left, negative. If there's an angle involved, we need to know the components of those velocities. So bear in mind, we're still working with vectors here. If there's more than a couple of particles involved, we've got to know each individual particle's momentum and then sum that up. So that on the left-hand side, what this stands for is all of the momentum of the system prior to interaction, and that stands for all of the momentum of the system post-interaction. Now, recall that we got to the conservation momentum principle by rearranging the second form of Newton's second law, F equals delta P over delta T, and we found that if we set the external forces equal to 0, that led to an expression that the final momentum equaled the initial momentum. If an external force in fact does exist, then obviously we can't set that F equal to 0, and as a result we can't expect the momentum to not change. In other words, if F here is not 0, then there's an external agent acting for a certain amount of time, and that agent is responsible for the changing momentum. So the momentum is changing as a result of this external force that's acting on that mass for that amount of time. This is known as the impulse momentum theorem. The left-hand side is called the impulse. The force acting for a duration of time is an impulse. And the right-hand side, of course, is the change in momentum. You can actually, if you have a graph of a force as a function of time, then the left-hand side can be graphically represented as the area under the curve of a force plotted as a function of time. For example, here's a problem in which we have an object being dropped from a certain height, 15 meters, and as it falls, it gains velocity until just prior to impact it has its maximum velocity, and then the impact with the ground lasts for a half a second, and we'd like to know what is the average force exerted on this object as a result of this collision. Well, we see the information we know is it has 2 kilograms of mass, falls from a certain height, the collision lasts this amount of time, and of course we're starting with no velocity when we drop it from 15 meters. We're using the impulse momentum theorem because we're desiring to find the force that is acting for that time span. Well, if we're starting with 0 velocity, we have no momentum at the top, so this expression can be rearranged so that we can calculate the force as the final momentum divided by the time of collision. Final momentum is the mass times the final velocity, and the final velocity can be calculated from your kinematics formula. The v squared equals v0 squared plus 2ax relationship. And when we do that, we find that the velocity that it strikes the ground with is 17.1 meters per second. Therefore, our momentum at that point will be twice that, or 34.2 kilogram meters per second. Dividing by a half gives us 68.4 newtons of force that's applied to the object. Now, let's bear in mind that what's going on here is that this force is being applied against the object's velocity. It's decelerating this object so it comes to a stop in half a second, because our conditions were that the object came to rest, it had a maximum velocity just prior to striking the ground, which we obtained by analyzing the free fall of this object. So applying the 68 newtons of force is the average force exerted on the object to bring it to rest in that short half-second time interval. So that's the application of the impulse momentum theorem. We will... Okay. I don't seem to have an end button here, and I don't know why. And I wish to end this presentation. And it doesn't seem to want to end. Okay. We're obviously going to have to edit this one if we can figure out how. Let's see here. Well, that's very strange. There's no end in sight. Pause recording. Insert new slide. Okay.